All right, so we've talked about different types of compounds, ionic compounds and covalent compounds. We're talking about solutions in this chapter and intermolecular forces. And the one thing that's kind of crosses over a lot of these is the bonding that occurs within metals. A lot of metals are solid. Mercury at room temperature is liquid, but there's something that's holding all these metal atoms together, and so we want to talk about what that is. And then the other thing we want to talk about is this idea of a solution of metals. And this is kind of weird. We don't usually think of solutions as being solids, but we can form a solution of metals, and we call those alloys. I'm sure you guys have heard of alloys before. So we got to talk a little bit about those, how they're formed, and what the structures of some of these alloys look like. So when we talk about metallic bonding, the model that we usually use is called the ELECTRON-SEA model. And so you see a picture at the left here. This ELECTRON-SEA model imagines that the metal atoms, we have these inner core of electrons. We have a positive nucleus, but then what's kind of unique to metals is that their valence electrons are held very loosely. And so if we have a whole bunch of metal atoms that get together, these valence electrons can, freely move between the atoms. So, we can imagine these, being able to move all around here. And what will happen is the positive, these positive core cations, they'll be attracted to these negative charges. And it's this attraction to the sea of electrons, so this freely flowing sea of electrons. These electrons are kind of like the glue that holds it all together, and this attraction between the positive cations and the electrons holds everything together. And so the strength of this attraction kind of determines the physical properties of the metal. And also the other thing that occurs is these cations, they form very orderly arrangements. So when we look at metals, it's actually crystalline. There's an orderly three-dimensional structure in the metallic solid. And this model of bonding, the thing that, this model that holds all of these cations together, explains a lot of the properties that we see in metals. And so one of the things we know about metals is that we can pound them out into sheets, we can draw them off into wires. And the reason why that is because these positive cations can slide past each other. In other words, I have this row right here, and I have this row right here, and they can move back and forth without ever coming into contact with each other. So, these electrons kind of hide them from each other, and so they can slide. These rows can slide past each other, and that allows them to slip, and allows them to get flat, and allows them to draw on the wire. And they can do this without shattering, because in an ionic compound, if you remember, we have a crystalline structure. But if we try to shift the rows over, then a positive ion will get next to a positive ion, or a negative gets next to a negative, and that's a repulsive force, and the whole thing shatters. And metals don't tend to do that. So anyway, the sea of electrons explains, malleability and ductility. And the other thing that explains is why metals tend to be thermally and electrically conductive. So we learned about temperature. We learned how temperature is the measure of the average kinetic energy of particles. And so, if you think of these loosely held electrons, if you start to add thermal energy to one side, they're going to start shaking around and bump into the next one, and bump into the next one, and soon it conducts heat throughout the whole metal, very rapidly. And I think electrical conductivity is easy enough to understand. These electrons can move. They can react to an electric field. They can move through the metal, kind of just jumping from one cation to the next. And so it can conduct a charge to the metal. The other thing, and I didn't put this one down, but I think it's kind of cool, is metals are shiny. And so the reason why a lot of metals are shiny is because when light hits them, these electrons, these loosely held electrons, can start to shake back and forth. And we learned in the previous chapter that when charges are moving, they can emit light. And so they will emit light at the same frequency that hits them. They kind of ring like a bell, and then it re-emits that frequency. But these electrons, they're free to move back and forth in this ELECTRON-SEA model. And so this also explains why metals are shiny. Okay, so that's a very, metallic bonding is very, this is pretty much all there is. This is the only model we have of it. It's much easier than covalent bonding with all the Lewis structures and stuff. But when we start thinking about solutions of electrons, we start talking about alloys, and we have to look at this crystal structure a little bit more. So alloys, as I said, it's a solid solution metal. So we combine either two different types of metals together, or maybe a metal with a non-metal, and we get different types of alloys. The reason why we form these alloys is because very often their physical properties, such as their tensile strength, how much stress they can withstand without bending or breaking, melting and boiling points, density, these things can change and be different in the alloy compared to the pure metal. So when we talk about alloys, there's two types of alloys. There's a substitutional alloy, and then there's what's going to be called an interstitial alloy. Now for the substitutional alloy, what we do is we take two metal atoms, and these metal atoms tend to be very similar in size, or at least pretty close in size, I guess, and one atom will replace another in the crystal structure. So you can see, if I have this crystal structure of copper atoms right here, and I were to mix it, and I think in this case it is indeed nickel. So if I mix it with nickel and copper are pretty close in size, atom-wise, and so this nickel can just replace the copper. And you can have, very often you have like varying ratios of the two, and different ratios have different properties. And we know this, from brass and bronze, that we can mix different proportions of metals, and we can get different properties in the brass. So that's pretty straightforward. For a substitutional alloy, we have to have two metal atoms of pretty similar size, and one just replaces the other in the crystal structure. Now, interstitial alloy is a little bit trickier to understand. So again, remember when we have these metals, we have this crystal structure. And so if we imagine, oranges, and you're piling up oranges in a pyramid, there's going to be like these little spaces between the oranges, between these spheres that you're packing together. And so if you have large metal atoms, metal atoms with a large radius, you can imagine there's a small atom, maybe like a carbon or nitrogen or even a hydrogen, that can kind of slip in there. It can occupy these small, what are called interstitial spaces, and that's where we get the name from. And so you'll have these metal atoms, and then you'll have these little atoms kind of fitting in there. And this can also change the physical properties. It can make stuff stronger. It can make it, possibly corrosion resistant. It can, change melting and boiling points. And so this is the other type of alloy. So when we talk about substitutional alloy, you're looking at two metal atoms close in size. If you have that, it's going to be more likely than not a substitutional alloy. And if you have a metal and a non-metal, and especially if they're different size, then it's going to be an interstitial alloy. And so you'll have the metal atoms, and then you'll have these little atoms kind of stuck in the space there. And so that's pretty much all there is. That's metallic bonding, that's alloys. And if you guys have any questions, we can talk about it in the next class.